Hello? Can you guys hear me? Oh,
Yeah, we can hear you. We're live
oh,
right
okay.
now, but apparently our opening videos aren't playing properly. And everyone just watched me sit here for a little while. Just a second. Don't touch anything. Nope, it doesn't want to work.
What are you trying to play?
I'm just trying to play our opening video, and it's not happening.
Oh, was it working last time?
It works all the time, pretty much. Well, that worked, although it's not counting down to anything really. Just a second. Huh. Yep, our opening videos just aren't working properly. Okay. Um, All right, well, let's just give it another 2 or 3 minutes for people to trickle in. I'm sorry about that. This is the first time we've ever had technical difficulties with StreamYard. Um,
Jeremy, I think you muted yourself.
can you hear me?
Now I can hear you. I think you muted yourself, Jeremy.
No, I'm still here. Can you not hear me?
I can hear you, Jeremy.
All right, trying this again. Everything crashed. Um, for the other people that are behind the scenes right now in StreamYard, can you not touch anything? Because it feels like someone else is trying to do something right now. Um, am I back? Can people see me now? Brandon, you still here?
Yeah, I can see you now.
Okay, something didn't work in the back end. Um, but we're almost 5 minutes in now and 5 minutes of technical difficulties. So I think we're just going to make the announcements and get started. Um, and I'm just getting a flurry of messages all over the place from people telling me what they're seeing. Okay, so welcome everyone. Sorry for the technical difficulties at the start of the meeting. I was seeing things that you weren't seeing, and you were seeing things that I wasn't seeing. So this week we've got another workshop. We're doing Shellcode. Brandon's going to be taking us through that. Just before we get to that, though, a few announcements. Magpie CTF is now just about 2.5 weeks away. That's starting on the 19th. That's the second weekend of Reading Week. So the last weekend, we'll have a full week off, and then we have our CTF. It starts Friday the 19th at 4 p.m., goes for 2 days, 48 hours until 4 p.m. on the Sunday, and then we do prizes. There are going to be companies involved. They're going to have space there at the CTF, thousands of dollars in prizes, giveaways, draw prizes. It's going to be a lot of fun. There's going to be movies and music, and we want you guys to work together, but we also want it to be a kind of online hangout where people can interact. But remember, it is always a competition. Lots of people are signing up. The word is getting out, and we have people starting to sign up from Toronto now. So yeah, Magpie CTF. I'm expecting that most of the people here are probably already signed up, but if you haven't, please consider it. Second announcement is next week is our third speaker in our speaker series, Adam McMath, who's the cybersecurity general manager at the Calgary Airport Authority, is going to be doing a whole workshop on threat intelligence. So essentially figuring out who the bad guys are and what it is they're doing, any of the techniques they're trying to use to break into systems. It's not only going to be a talk, though. He's got some hands-on portions that he's built. We've met him before. He's a really awesome guy, very interesting. I think his talk and I'm going to say like mini workshop, because there's going to be some hands-on stuff, is going to be awesome. We're really looking forward to it. So that's next week here. Remember, that's only for people that are paid members of the club, but you can still sign up to join. It's $5 at this point for the second semester of the year. So $5 will get you access to this workshop, to this speaker and for the next two speakers that we have. After Adam comes Dr. Joel Reardon from the U of C talking about privacy and COVID tracing apps. And then Emily Vincent talking about hiring in InfoSec. So yeah, next week is Adam. We hope you all join. I think it's going to be an awesome talk, and there's going to be some fun stuff for us to try out. So that's everything that's on the horizon right now. CTF in a few weeks and a speaker next week. Otherwise, I am going to leave it to Brandon to take over for this week's workshop. Thanks for coming, everyone.
All right. Hi, everyone. Let's get started with the workshop. So today we're going to be doing 64-bit shellcode for x86-64 architecture. Just a second. Just pause this. Okay. Yeah, we're going to be doing shellcode. So our goals for today are going to be learning what shellcode is, how to build shellcode from scratch, and learn to execute shellcode in a buffer overflow. Some relevant courses for this workshop are computing machinery, so CPSC 355 and 359, as well as principles of computer security, CPSC 525. The tools we're going to be using today are GDB, strace, Python 2, object dump, assembler, and the linker. Some of the prerequisites for this workshop are here. I'm going to go over them real quickly. We're not going to be covering them in detail, so hopefully you're already familiar with this. It's going to be strings, characters, bytes, bits, ASCII, buffers, stack, buffer overflows, and some C, C++ programming, not a lot, honestly. Okay. Oh, right. Make sure to fill out the attendance form, guys. I think Jeremy's going to post that in the chat, so just make sure you fill out our attendance form. Okay, so let's go through some quick review. First of all, we're going to be using the AT&T syntax, which is the default syntax for GNU assembly, or GAS for short. Now let's actually do some x86-64 assembly review. If you remember the register usage, RAX, RCX, all that stuff, these are considered caller save registers, meaning that they're not necessarily saved across function calls. So if you think of these registers as like a variable, like x, like let's say RAX is just x equals 1. X equals 1 is not going to be necessarily saved across function calls. Or in other words, they're just general purpose or scratch registers. By convention, rex is used to store a function's return value, but we'll get a bit into that a bit later. As for registers RBX, RBP, and R12 to R15, these are callee save registers, meaning that they are saved across function calls. In simple terms, it means they are reserved. And register RSB is used as the stack pointer, and it points to the topmost element of the stack. Register RBP is used as the base pointer, and it's a pointer that saves the stack pointer to use the return instruction. That's not super important, but I guess we should just briefly go over it. So that was just some quick review. Is there any questions about that? Is everyone okay with that? It's okay if you feel a little bit overwhelmed with the review. Okay, I'm just going to move on now. All right. So there's also the last bit of review, which is Indianness, which is just the order you store bytes in. So, for example, big Indian, you just store the bytes as is, so 0A, 0B, 0C, 0D. Whereas in little Indian, you store from the back. So you store 0D first, then 0Cs, and then 0B, then 0A. So that's Indianness. All right, so let's finally get into the actual uh, workshop. Part 1, shellcode construction. What is shellcode? Shellcode is typically a small piece of code that is injected as a payload to exploit a program vulnerability. It is often written in machine code. Machine code is just any type of assembly code. And this term has since become a bit of a misnomer because shellcode doesn't necessarily just spawn a shell. It's not limited to shell spawning. You can do a lot of things with shellcode, such as, I don't know, print a statement. But in terms of like attacking, you could do like a reverse shell, or you could inject a keylogger, things like that. So it just depends what you can do with what you have. It depends on the context, basically. Okay. Now, how do you write shellcode? Well, some assembly is required. Yeah, I know, I'm hilarious. Okay. So shellcode is made up of opcodes or operation codes. Opcodes is just the short term. All assembly instructions correspond to a byte or sequence of bytes called opcodes. Let me see if there's any questions so far. Okay. So these are some example opcodes, as well as opcodes you should memorize. So for example, a system call. The system call, to do a system call in assembly, you just write syscall. And the syscall instruction corresponds to these 2 bytes, 0x0f, 0x05. So these 2 bytes correspond to the syscall instruction. And you also have the no operation instruction, which is kind of funny because it does nothing, but it's still an instruction. So the no op, when you're writing assembly, it's just written as NOP. And this instruction corresponds to the byte 0x90. Is there any questions on that? Does everyone sort of at least have an idea of what an opcode is? If I'm going too fast, please let me know. Okay, I'm going to be moving on now. So that's what an opcode is. Okay, so for exercise 1, you're just going to be trying to figure out what this piece of code here translates to in terms of opcodes. So what sequence of opcodes does this assembly code translate to? You should be able to do this fairly quickly. You can find a program in exercise 1, and you can either Google these instructions, or you can also do a command. There's a command that can tell you this type of thing. So if you just do a little bit of Googling, you shouldn't have too much trouble doing this. I'm going to give you like 2 to 5 minutes now. Sorry, my bad. I realized I didn't put the slide that tells you what to actually do. So this is the exercise. And yeah, if you have any questions, just type them in the comments, please. Also, sorry, I forgot to say that Orchid is not going to be giving out points for this tonight, mainly because I didn't have enough time to put the flags. But yeah, just uh, just a heads up for that. That doesn't necessarily mean you're wrong. Just gonna wait about 1 more minute, and then we'll go over the solution. Okay, let's see if there's any questions. Any tips for how to convert this bytecode? Okay. Any tips for how to convert this bytecode? You can convert the bytecode by. Actually, I'm not sure what your question is, Jeremy. If you're talking about how to convert the assembly instructions to bytecode, like I said, you can Google like each instruction, like for example, push RBP and then opcode, and that should give you some results, and then move RSP, RBP, that should give you some results. Sorry, opcode, yeah. Or there's another command that we're going to go through in just a second. Okay, so let's go through the solution. Sorry, I forgot there was a hint, but yeah. The hint was the right tool is in the tool list for this workshop. So if you looked at the tool list, you should be able to figure out which command is the one that can give you this information. Okay, so the solution is to just, like I said, either Google each instruction or run object dump on the binary. Pretty much any binary can work for this. So let's go into example. Okay, so a.out is a binary. So if I run object dump -d, that's a tag, and then a.out, it's going to spit out a bunch of stuff. If we go to main, then here we can see the opcode sequence. So it's going to start with 55, followed by 48, 89, and E5. So this is what you would have given to ORCID, for example. Is everyone clear on what opcodes are so far? If not, it's okay to ask questions. Please ask questions. I'm going to move on now. Okay. So now let's actually get to writing some real shellcode. Now that we know where it actually comes from. Let's make a short assembly program first and turn it into shellcode. So let's go do that with in the terminal. Okay, example 2, I think. Yeah. Okay. So you have the, oh wait, no, it's not this one. Give me a second. Okay, here we go. So we have this shellcode. It's very simple. We're just moving the argument 21 into RDI, and then we're moving 60 into RAX. Wait, is this the right one? Sorry. Okay, no, there we go. My bad. That's the next example. Okay, so here we are. This is a very simple program again. We're just putting the argument 0x1337 into RAX, and then we're returning. Okay, so what does RAX do? It's, like I said before, it's usually the return argument for a function. Specifically, it doesn't matter. It's just the return value. Anyway, if we, sorry, I'm losing my train of thought. Let me go back to the slides. Okay, so first we can compile the shellcode with AS, our assembler, and then link it. So I already have this done with my makefile. So if we go into makefile, I already have this done. So I'm calling the assembler, which is AS, and then I do shellcode.s, which is the shellcode, right? It's this shellcode right here. Then I just say put it into this file called shellcode.o, and then link it with ld, the linker, shellcode.o, and output it into the binary shellcode. So shellcode is our shellcode, and it does nothing right now. So now we can do object dump. -d shellcode. And this opcode sequence right here is going to be our shellcode. Okay, so let's try to put it here into opcode. And now I just created this file called opcode. We're going to delete everything that we don't need and just keep this sequence. Actually, we'll just keep that just for a good visual. So this is our opcode sequence. These bytes correspond to these instructions. And if you see our shellcode program corresponds to the exact same thing. Move this literal into REX and then return. Move the literal into REX and return. Okay. Now you also have a program called shellrunner, and shellrunner is very simple. All you got to do is put any byte sequence, any shellcode, into this code buffer. So once you put it in this buffer, you just close it with 2 quotes, and then you compile shellrunner with this. You want to make the stack executable on shellrunner, and then you output it as shellrunner. I think I included make files, so you can just run make on it, and it'll make everything for you. So let's try. Let's go back for the slides for a second. So yeah, I just went over this. This is our shellcode. Okay, but can it even run? Like, there's no point in making shellcode if it can't actually run anywhere. And yes, the answer is yes, but you don't have to take my word for it. We're gonna run it in a second. And like I already said, you can compile it with make because I included a make file, or you can run GCC with this input. So let's look at what it actually does. Shell runner, and there we are. That's what it does. So to give a bit of an explanation of what's happening, foo here is a function pointer. So we're turning this code buffer into a function with a function pointer. I'm not going to get into any specifics of this, but basically we're printing the return value of this shellcode, right? And if you remember, our return value is this 0x1337. So what is 0x1337 in decimal? It's 4919. So our return value is this number because we put it into REX, which is the register for the return value of a function. And when we run it with shellrunner, it gives us 4919, which is 0x1337 in decimal. Was that unclear? The goal of compiling the shellcode, binary and running object dump was just to get the opcodes for shellrunner, right? Yes, that's correct. So we're compiling the shellcode binary to, like I said, run object dump and get these opcodes. So if we look at shellrunner, this is the same shellcode. Oh wait, is it? Actually, no, it's not, but we can change it. It doesn't matter. I'll write it right now. 0x48, 0xc0. Wait, is that how you write? Yeah. Okay, so let's do 48, C7, C0, 37, 37, 13, 0, 0, 0, 0, and then C3. Okay, let's compile that. shell runner. And there we are. See? So I took the opcode from object dump. I put it into the file opcode. I copied those opcodes into this buffer, and then we executed it as a function pointer. And I printed the return value, which gives me 4919. So hopefully that answers your question. Okay. I'm going to move on now. If there's any other questions or if you need me to slow down, please let me know. Okay, so now part 2. Let's actually do something interesting with the shellcode, not just return something. Let's do a system call shellcode construction. So this is a very basic overview of how system calls work in Linux. System call is basically just how a computer program requests a service from the kernel of the operating system on which it is executed. So system calls are executed via a lookup table called a system call table. So what happens is, for example, you're in a user mode. You're writing a normal C program. And in that normal C program, you can call something like open, right? Maybe you're opening a file to see what's in the file. So you call open, and open actually has a wrapper. And this wrapper is what handles the call to the this wrapper is what handles the open call. And what it actually does is it sees that you're trying to call open, and then it tells the operating system, hey, can you open this file? And then the system call, the operating system goes and tries to find the open system call, sysopen, and then gives that back to you. So that's how a system call works. And the operating system does this by numbers. So each system call has a specific number for it. And that's how it is able to look up the right system call for what you're trying to find, for what you're calling. So does that make sense? I'm going to move on now. Okay. So system call table. I want you guys to go to this link. I'm going to post it in the chat. Whoops. Give me a second. Nope, it's not. I'm going to post it in the chat. Don't worry, it's not like a malicious link. But go to this link. And this is the system call table for 64-bit. This is a very important link, so make sure you keep this open in a tab or something. This is going to be important for the following challenges. Okay, so for our purposes, we will be using the instruction syscall as opposed to int80. This might confuse some of you, but don't be confused. Syscall is just the system call instruction in assembly for 64-bit, whereas int80 is the system call assembly instruction for 32-bit. But that's not important because we're using syscall. But and that means that we're going to be using the 64-bit syscall table. For example, these are the numbers corresponding to which system call. So for example, 0 corresponds to read, 1 corresponds to write, 2 to open, 3 to close, and so forth. Okay, is that clear? I hope that's clear. Okay, and now this other link is also very important. So make sure you have this link open in a tab because it's going to come up for the following challenges. This is the system call register convention. So whenever you do a syscall, where you put your arguments matters. So you can't just put whatever you want into RDI, RSI, and RDX and expect the system call instruction to know what you want. So there is a specific convention, and it's this. The system call rex is where you're going to put the system call you want. So for example, if I want to do a write system call, I'm going to put the number 1 into rex. And then I'm going to give it RDI. So maybe like what I want to, let's say I want to print something. So I would give it rex as 1, and then I would give it RDI as, I think, 1 as well, because 1 is, I think, standard out, if I remember correctly. And then I would give it a string for RSI. And that's that way it's going to know, okay, you want to do a write system call from rex, and you wanted to go to standard out from RDI, from the number 1 in RDI, and you want to print the string hello world. Okay, I know what you want to do now. And that's what the system call register convention does. Is that clear? I'm going to move on otherwise, if there's no questions about that. Okay, so let's go through an example. Exit 21, system call shellcode. So find the system call. This is how I would go about the process. So we find the system call for syscall number for exit. We figure out the arguments it needs for exit, and then we assemble it. So that means we do what we did with the previous shellcode. So we compile it, and then we extract the opcodes. So let's actually do that. First, let's go to this link. Let's find, I know this is probably hard to see. I'm going to zoom in. Let's find the exit system call. There it is. Exit is 60. Right? So this is why this link is going to be important for the future exercises. Okay, so we found exit. We got that. Let's write it here. Let's go to example 2. So exit system call is equal to 60. Okay, we got that. What's next? Next, we want to figure out the arguments needed for the exit system call. So how would I do this? Sorry, I cut off there for a second. My mic went off. Okay, so how do I figure out the arguments for a system call? For exit, I would man the page. So let's do that. Man exit. Actually, I think it should be man to exit. And the 2 is because you're specifying that you're looking for the exit system call. So here we just have one argument, which is the status, int status. It's an integer. And yeah, that's all we need to know. So let's figure it out. So we would put the number 60 into rex, and then we would put the status code into RDI, right? Because it's the first parameter. And since exit only has one parameter, then we just need to put an integer into RDI. So let's do that. Okay. Okay, and arguments, let's say, is just arg1 is equal to integer. Okay. Let's go to the shellcode. So that's what we're going to do here. So in this shellcode, I'm going to move the exit status 21 into RDI. It doesn't matter what number that is. It just matters that we put something a little bit distinguishable, right? So like if you put 0 or 1, it's kind of hard to know if that means anything. And then we're going to put 60, which if you remember is the system call number for exit. And we're going to put it into REX, which is where we put the system call we want to execute. And then we call syscall. Okay, so let's compile it. So remember, you can follow along with me for this. You have all of these examples in the files to download. Oh. Oh, okay. So what does man exit return then? Man exit will return the command line utility. So let's actually take a look at it. Man exit. So exit cause the shell to exit. So this is just the command line utility. The exit utility shall cause the shell to exit from its current execution environment with the same status specified, blah, blah, blah. If you do man, you'll actually see what each number means. So man1 is the executable programs or shell commands, which is what which is the default. So if we do man1 exit, you'll see that it's the same page we got earlier. So man exit, it's the same page, right? Now man2 is for system calls, and that's what we were looking for. That's how we figure out the arguments. So this is actually pretty important detail, so you probably want to write this down somewhere. Man2 is for system calls. Anyway, thank you for the question. I hope that was clear. Okay, so let's go back to shellcode, compiling the shellcode, right? So let's look at my makefile. Here in my makefile, we compiled the shellcode the same as always. Shellcode.s and then blah, blah, blah. So let's make it. It's already made, so I'll just clean it, make again. Oh, whoops. Give me a second. Actually, if you make it, you might have, I think you will have an error. Just because I accidentally named extractor.py e.py in my makefile. So if you're getting an error, just make sure to rename extractor.py to e.py. Example 2. Let's make it. Okay. So we made shellcode. It does nothing, right? It looks like it does nothing. So we'll get that we'll get into that in a second. But it does do something. It's just that we can't really see it by normal means. But first, let's extract the opcode sequence. So object dump -d shellcode and pipe it into opcode. So this entire opcode sequence is going to be our shellcode this time. So let's look at shell runner. And here we are, and it's the exact same opcode sequence, as you can see. So we have 48, C7, C7, 15, bunch of nulls, and so on. Okay, but typing that out by hand it's going to get tedious, especially if you're experimenting with different types of shellcode or you're doing something a bit more complex. So let's not type it by hand. That's why I've included into your files to download an extractor, which will do it really neatly for you. So if you do object dump -d, the binary, actually we'll do -d. Wait, is it? Yeah, no, it doesn't matter. Object dump -d shellcode, and then we pipe it to /e.py. Oops, give me a second. There we go. We do Python 2 specifically. That's why I asked you guys to get Python 2. And it's going to print it out all neatly for us. Isn't that convenient? So we can put this and pipe it into our opcode file. And now we have very neat opcode sequence. And it's way more convenient than trying to type it out by hand. And trust me, even like a couple lines, it gets annoying. And you might even mess up your shellcode without knowing. So it's better to automate it and make sure you're doing it correctly. Okay, so now that we have the shellcode running and we have the shellcode actually copied in shell runner, oops, that's the binary. Oh, sorry, I got a question. Why Python 2 specifically? No reason. That's just the script I found. Because if the script is written in Python 2, Python 2 and Python 3 are a little bit compatible, but not very. So if you try to run the script with Python 3, it's not going to work. Okay, where was I? Right, we were going to see what the shellcode actually does. So let's do that now. Let's go back into the presentation for a second. Okay. So this is what I just went through. That's a handful of shellcode. Typing that with /x especially is just painful. And luckily for us, we don't have to. So use the Python script, extractor.py, just like this, and it's going to make it really convenient. We plug and run. So I just showed you that I put that shellcode sequence or that opcode sequence in code. And again, we put it into this function pointer that's going to call it. So compile it, make sure to make the stack executable because this code is it's not supposed to be executable and it won't run if you don't compile it with the exec stack. And what? Nothing happened? Well, not exactly. Something did happen. So let's strace shellcode first. So it exited with code 21. Let's look at our shellcode. What does it do? It puts 21 into RDI, the first argument to exit, right? First argument to exit, put it into RDI, and then you do the system call. So you put 60 into REX, which is the exit system call. And that's exactly what this code does. It exits with status code 21. Let's do the same thing for shell runner. So shell runner has a lot more stuff, but it's all just junk, right? We're not really interested in all of this. This is mostly just overhead, I guess you could call it. It's basically setup because it's an actual full binary. It's not just assembly code. But let's look at this. At the very end, we exit with status code 21, which is what we wanted, right? And I can even prove to you that we're exiting by doing this. So let's try to exit, print. Let's try to print something here. Print fake news. Okay, let's make that. Oh, whoops. I've been looking at too much Python. Printf. Okay, there we go. Now let's do strace. Actually, let's run shell runner first, see if our print statement actually works. And it doesn't actually print our print statement. And why? Because we're already exiting. We're calling the system call exit, so it's not going to be able to get past that piece of code. So let's strace it again. And as you can see, we're exiting with status code 21. And it won't print our fake news print statement. Okay. So if there's not any questions, If there's no more questions, I'm going to move on again. And you're going to be doing an exercise soon. Okay, so let's try something a bit more tricky. How would you perform a write to standard out system call? There's two issues to consider when writing shellcode. The first one is nulls, null bytes, which is 0x00. Null bytes are common, they're a common forbidden character in shellcode. So if you think something like string copy. Actually, I kind of want to ask you guys, does anyone know why null would be something that you don't want in shellcode? Does anyone know? And like I said, think string copy. What does string copy do? How does it stop? Yes, exactly. So it terminates strings, right? And if you're writing shellcode and let's say you're exploiting a string copy based buffer overflow, then your shellcode is not going to be fully injected because it's going to terminate prematurely if you have a null byte anywhere in the shellcode, right? So you have to be careful with null bytes when writing shellcode. But like I said, it depends on the situation. If you have a different function that maybe doesn't care about null bytes, but maybe it terminates on new line, then you have to be careful with new lines. Null bytes are just the most common terminator character, so you have to consider that as an issue. And the other issue is you can't use static addresses unless you know where it is in memory. So when you're writing a shellcode and you're specifically exploiting a buffer overflow, you don't really know where your string is going to end up, and you don't really want to rely on that. So I won't ask you about that question because it's a bit more complicated, but if no static addresses, then how do you get the address of any string to be able to write? Okay, so now it's going to ramp up a little bit, and this is going to be a bit harder to understand. So it's okay if some of you don't get this. Yeah, okay, so I'm going to try to explain it as best as I can. So if you recall the return-oriented programming workshop, it's a similar idea in terms of like trying to build up a stack. It's a similar concept, except this time we're going to be using the push instruction and the register RSP, which is, if you remember, is the stack pointer. So here's our string that we're going to be trying to print. So we have hello with a cap with an exclamation mark, which translates to 48, 65, 60, 60, 6F, 21. Okay. So first we're going to move hello into R11. The register R11 is not relevant. You can replace R11 with more or less any other register. It doesn't really matter for our purposes. I just chose R11. Then we're going to push R11. So what does the push instruction actually do? It pushes whatever argument on the stack. Give me a second. Let me just look at my... Yeah, so the push instruction allocates 8 bytes and places the source onto the stack. So we're placing hello, this hello string, onto the stack, right? That's the first thing we're doing. Then we push RSP. However, we haven't put anything into the stack pointer, like it's just the stack pointer. So what that actually does, it's allocating 8 bytes, right? But 8 bytes of what? There's nothing there, right? It's just the stack. So what that actually does is it subtracts the value from the 8 bytes from the value of the stack pointer. And eventually what that gives us, it gives us an address. So it's almost like a pointer. We're almost like creating a pointer. So here's the hello string. And then because we are subtracting 8 bytes from the stack pointer, we're actually just creating here an address that's pointing to this string here. And when we pop RDI, we are loading the value of RSP, an address, into RDI. So the address of RSP is in reality the address of our string. So this, remember, the stack grows downwards, right? And when we pop something, we're actually popping something off the top of the stack, right? When we pop RDI, we pop whatever's at the top of the stack. What is that? It's going to be this stack pointer minus 8 bytes, which is an address pointing to our hello string, and that address is going to go into RDI. Okay, and behind them, right, sorry. And then other than that, that's kind of like the gist of it. Is there any questions? Like this is a bit complicated, a little bit hard to understand. So please ask questions if there's anything that you're having trouble understanding. Okay, I'm gonna move on now. So now, besides those instructions, does anyone know why I might be doing DIL and AL? So DIL is the, I think, 1-bit. Wait, let me check. Give me a second. Sorry, it's the 8-bit version of Oh, sorry. Okay, so Emily has a question. Okay, so what's the end goal here? It seems like an awfully complicated way to get the value into RDI. So the point of doing this, yes, you're right. It is a very complicated way to get a value into RDI, and that's for a reason. Remember, we're putting an address in RDI. We're not putting hello string. We're putting an address, the address of the hello string here. How else are you going to put that address if you don't want to rely on static addresses? There might be a way, like, I don't know, maybe if you're like really smart, but this is just the simplest way to get this address that's pointing to hello into RDI without it being static. So none of this here is static. That's the point here, right? Push R11 like isn't static. It doesn't matter where it is in memory. And then it just matters that we push whatever we wanted to R11, and then we push RSP in order for it to point to this string. That's the point. So I hope that answers your question. Okay. Oops. All right, I'm going to move on now. So I'm going to ask again. DIL and AL are the 8-bit versions of RDI and RAX. So does anyone know why I would want to do that? Why would I want to use the 8-bit versions of these registers? If you remember the issues that we have to consider, it's one of those two issues. Which one is it? So remember, the two issues to consider are null bytes and that we don't want to use static addresses. So why would I want to use the 8-bit versions of the registers? Okay, I'm just gonna move on then. So the reason why is because RDI, the instruction move the literal 1 into RDI, is going to create null bytes, specifically because we're using the 64-bit register, the 64-bit version of the register. That's going to create null bytes for us, and we don't want null bytes. So we're trying to get rid of them, so we're going to be using the 8-bit versions of these registers. Now, how do you know that that you want to use the 8-bit versions? Well, you kind of just play it by sorry, by site, right? So for example, let's go to example 3, I think. Actually, no, it's not this one. Actually, I think I'm just going to go back to just find it. Okay. Okay, I'm just going to use this as an example, actually. Okay, so let's go into shellcode.s. This is the one of the exercises or examples we did earlier. So let's look at the opcode sequence of that one again. We're in example 2, right? Yeah, we're in example 2, sorry. Okay, so if you see, we have a bunch of null bytes, right? We don't want null bytes, so let's try to do DIL, and what was the other one? AL. AL. So let's do make. Am I in the right place? Should be. Oh, that's why. There we go. Okay. There we go. We made it. Okay, now let's look at the opcode sequence. So in my make file, I already called the object dump and put the shellcode into Python 2, and then the extractor.py. So let's take a look at the opcode sequence. Well, would you look at that? We got rid of all the null bytes. Why? Because the 64-bit versions have more space or something. Honestly, I actually don't know. But the point is, DIL and AL will avoid null bytes in shellcode, and that's something we want. Okay, so if there's no other questions, oh, sorry. Oh, okay, Jeremy answered earlier. Yes, that's all correct. Yes, we don't want null bytes in the shellcode. Okay, so if there's no other questions, I'm going to move on. Okay, so now for exercise 2, I want you guys to complete the assembly code for the write system call and give the opcode, well, not, that doesn't really matter, but yeah, just try to complete the write system call for exercise 2. I've already given you most of it, so let's go take a look. Just before you start, exercise 2. Sorry, not that one. Sorry, exercise 3. There we go. Okay. Nope, just kidding. Exercise 2. There we go. Okay, so hello syscall. Okay, so here's part of it. Don't mind this exit system call. This is just so your program doesn't segfault once it's done. But yes, yeah, try to finish this exit system. Sorry, this write system call. What this is gonna do is it's going to print hello to standard out. So if you're doing this in a terminal, it should print hello. Now, let's go back and just refresh your memory real quick. How I wrote the exit 21 system call. So you find the system call number for exit. You might want to write these steps down, by the way, just so you have something to follow. So you find the system call for exit, figure out the arguments needed for exit system call. So in this case, it would be figure out what the arguments are for the write system call. Remember man2. And then you compile it, and you want to try to put the opcode sequence, the final opcode sequence, into your shell runner. Exercise 3. Yeah, in your shell runner. So this is where you're going to want to put the opcode sequence. And then if it runs, then you've done it correctly. So I'm going to give you guys, I say maybe like till 7:20 for now, if there's no questions. Yes, I said that earlier. Sorry, let me just show it. Yes, I said that earlier. I accidentally named extractor.py, or sorry, I renamed e.py in my makefile, and it's actually extractor.py. So just make sure they match. So you can either rename extractor.py to e.py, which is the simplest because all my makefiles use e.py, or you can just write in the makefile extractor.py. Yeah, that's right. The examples use E and the exercises use extractor. Oh, actually, yeah, never mind. Oh, I see. Yeah, just make sure they match up. I'm sorry about that. But anyway, if there's no other questions, I'll leave you guys to do the exercise. If there's any questions, I'll try to answer them. I'll go to the exercise. Okay. And there's obviously, here's some pointers. Okay, I'm just checking in. How is everyone doing? Do you guys need more time, or should we move on to the solution? Or do you guys want a hint? If you guys want a hint, ideally, I'd like you to tell me kind of like where you guys are at, like what you might be having trouble understanding or trouble with. Man 2 isn't working on my terminal. Does normal man work on your terminal? Like just man and then, oh, sorry. So, yeah, like I said, it doesn't just man work without the number. If not, just Google it. It'll give you the same results. It'll give you what you need. It might be that you don't have the correct man database installed on your system. So just if the man2 command isn't working for anyone, just Google man2 and then whatever system call you're looking for. I think we all need to thank Callie. Okay, if there isn't any objection, I'm going to go over the solution. Going to give like a minute for anyone who wants to object to respond. Okay. Oh, what bar do I use? I use polybar. What bar? I think Varyun. Varyun means my taskbar or my, yeah, I think my taskbar. Okay, so I guess there's no objection to me going over the solution. All right, let's go through the solution. So I pretty much gave you the steps. You should have everything you need to be able to do this exercise. And I also gave, like I gave you sort of like the hardest part to come up with, because I know that assembly code is pretty difficult, and like trying to do hacky stuff with assembly code is even more tricky. So I'm just trying to streamline the learning process a little bit by giving you part of the assembly code. All right. So let's look at the code. This is what the code looks like. Actually, let's go through the entire process first. So first, let's find the system call number for write. Let's look at write. Where is it? I think it's at the very top. Okay, it doesn't want to find it. There we go. Syswrite is going to be 1. So we know that the RAX is going to be, so we know we're going to want to move the literal 1 into RAX. Okay, so that's done. Okay, let's look at the next step. Figure out the argument write takes. So let's look at the arguments for write. Man2 write. So remember, man2 is the system call manual page. Okay, so write takes a file descriptor, a buffer, or the sorry, an address of a buffer space, and then the size of the buffer. Okay. So let's see. Oops. Oh, what happened? Okay, there we go. So we're going to need to put a file descriptor in there. So if I remember, I gave you this little pointer that the file descriptor to standard out is 1. So standard out should print it to your terminal. So we're going to want to put 1 into, let's see, we're going to want to put 1 into our I forgot the calling convention already. x86, 64. Okay, here it is. So RDI, RSI. So we're going to put it into RSI because that's where the second argument goes. Oh, sorry, no, not RSI. We're going to put it into RDI because first argument, my bad. So we're going to put it into RDI. And then we're going to do put count, which is just, let's count these. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. Sorry. Wait, no. 1, 2, 3, 4, 5, 6. So it's going to be 6 bytes. 1, 2, 3, 4, 5, 6. Okay. So let's put that into the last register. And that's going to be RDX. Move 8 into % RDX. So let's see if that works. Let's make it extract that pi. Let's change this to e.pi. Okay, there we go. And let's try to execute shell runner. Oh, it's seg faulted. Probably got something wrong. Whoops, sorry, not shell runner, that's why. Shellcode, we want to execute shellcode. There we go, and it prints hello. That works. Now let's look at the opcode sequence. And it's not there. What happened to my makefile? Python 2. Okay, there we go. There's the opcode sequence. Now, I have a bunch of nulls. Does anyone remember why? Anyone remember why I have a bunch of nulls? Okay, I'm just going to keep going. Otherwise, we're going to take too long. Okay, the reason why I have a bunch of nulls is because I'm using the 64-bit versions of these registers that don't need that much space. So for example, RDI, we can change that. So let's look at the 8-bit registers. x86. Oops, not this. There should be a page. I don't remember if I included this link. I might not have, which is an important link, so I apologize. Yeah, I didn't include it. Shoot. . Sorry, I'm just trying to get the 8-bit register versions of these. Okay, here they are. I got them here. I'll post this link in the chat. Yes, there's oops. There is 32-bit versions as well as 8-bit versions um, of registers. So here I'll show them to you. So REX is the 64-bit version of the accumulator, and 32-bit version is EAX, 16-bit version is AX, and then the 8-bit version is AH. Sorry, the high bits of the lower 16 bits, and then the very first 8 bits is AL. So I'm guessing for like A low. Okay, so let's transform all these registers that we don't need all the space for into 8-bit registers. So RDI is going to turn into DIL. RAX and is going to turn into AL, and RDX is going to turn into DL. Okay, let's try it again. Let's cat opcode. Well, would you look at that? We have reduced the number of nulls. So let's actually compare the difference. Let's do that again. Give me a second. Well, let's do RDI, RAX, RDX. So let's move opcode into bad opcode. Let's go back to shellcode.s. And let's make that. Now let's look at both. So this is the difference. It also reduces the size of your shellcode by a lot, which can be important depending on how much size you have. So I still have 2 null bytes though, and I'm kind of wondering if anyone actually knows why that is. It's a bit tricky, but there is a reason why there's 2 null bytes there, and we can get rid of them. Does anyone have any ideas? I'm not sure what you mean by string terminator, Princess Grouchy. No, oh, I see. No, it's not a string terminator. Hello doesn't have any string terminator, but I'll give you a hint right now. Give me a second. I'm going to give you a hint right now. 1, 2, 3, 4, 5, 6. Any ideas? Yes, that's correct. The string is less than 8 bytes. So we're not fully utilizing the entire register. And it's causing null bytes in there. So let's try to add 2 more exclamation points, which is just 20. The ASCII code for exclamation mark is 21. So now we have 3 21s in there. Let's try to make that. And we got rid of all of our null bytes. If we try to look for null bytes, they are not there. Perfect. Now let's put it in shellcode.shell runner. Actually, let's make sure that our shellcode is still running, and it does. And now it's printing hello with 3 exclamation marks. Perfect. Let's go into exercise 2 from here. Okay, let's go shell runner.c. Let's go into opcode. Let's copy paste this here. And as we can see, I'm just putting the shellcode into this code. Let's make it. Actually, we'll stay here. Okay. Now let's try to run shell runner. Whoops. Okay, there we go. It's seg faulting. That's odd. Huh. Maybe I didn't write. No, I did. I'm wondering if maybe I think I. Give me a second. Let's try with just 121. I don't know why it's seg faulting. Let me look at my solution. Shellcode.s. No, sorry, this is a different one. Okay. Yeah, this looks like the same code. Let me just go change to my solution. Okay, let's try to paste this shellcode in there into shell runner. Oh, wait a second. Give me a second. No. Oh, I think let's actually look at the assembly. I might have missed an instruction somewhere. Okay, so we have move that into R11, blah, blah, blah. Then we're popping RSI. We are XORing RDX. Oh, actually, I think that's why. I don't think I XORed RDX. And I think we need to XOR RDX for this shellcode. And I think I can't remember exactly what the reason for needing to XOR RDX, but you do need to XOR it. Let's see if that works. Let's see. There we go. That works. Yeah. So it was just the XOR. Yeah, I honestly can't remember why the XOR is important, and I should have included it in your exercise because I it's something that you it's hard to come up with by yourself because uh, there's not really a clear explanation for it. And I can probably find one. You can probably find one if you Google it. But at this time, I honestly can't remember why you need to XOR uh, RDX. But yes, this instruction is very important. I'm guessing it's to clear the register uh, before you use it, because since we're using only the first only the first 8 bits of the RDX register, maybe there's some leftover things in the rest of the register, but that's my guess. Don't quote me on that. But anyway, yeah, we got shell runner to work, and we don't have any null bytes, which is exactly what we want. So let's go back to our presentation. Is there any questions on that? If not, I'm going to move on just because we're running out of time. Okay, I'm going to keep going. Now let's actually write some real shellcode. So for this, it's the same process again. Figure out step one, find the system call number for execve, figure out the arguments for the exit. Sorry, this should be, I think, execve for the execve system call. And second and third arguments for execve can be 0, so that doesn't matter. And this is what we end up with. This is real shellcode. This is used. This can be used for a CTF challenge, for example, such as Magpie CTF. uh, and this is actually almost the exact same thing we've been doing for the write system call. So we're moving this string, which is binsh, into the register R15. Again, R15 doesn't matter. It's not a special register. And then we push RSP, and then we pop RDI. We're doing the exact same thing we just did with this write system call. So again, instead of doing hello for a string this time, though, we're going to do // bin // sh. And that's because we want to execute that command. And again, we're doing the same thing. We're pushing RSP after we've pushed the string on the stack, and then we're popping it into RDI. And then we pop it into RDI because we are supplying execve. The first argument of execve, we're supplying it with the address of the string binsh. Okay, so let's actually just take a look at that real quick, and then we'll exercise 3. So here's the shellcode. So we push REX. I think someone actually gave me a reason why we push REX, but I can't remember it. I think it might have been to align the stack or something like that. But anyway, after that we XOR RDX, XOR RSI. Remember, let's look at man exec VE. Let's look at man 2 of exec VE. So the first one is const char path name. So this is the string. We want to give this first argument the string binsh, and that's what we're doing with this snippet of code, which, if you remember, is the exact same snippet of code from the write system call. And then we want to supply const char argv argument value list, and then environment variable. Honestly, the other two arguments don't even matter. That's why we're just XORing RDX and RSI, because RDX is argument 2, RSI is argument 2, and then RDX is argument 3. And we're just XORing them because it doesn't matter. They can just be 0. And then we are calling the system call number 59, which is execve. If we look at the system call table, execve, it is 59, right? The number 59, and that's the simple system call shellcode. Now for your exercise, you're going to add another system call right on top of that, first shellcode. And what this system call does is actually it's a very simple system call, but it's very powerful, and it's also really, really dangerous, which is why it's probably not as easy to execute anymore these days, but it's still really dangerous nonetheless. So what you're going to be doing is add the set REUID 00 system call to the previous shellcode in order to gain root. The set RUID system call will come before the call to execve. And by now you should remember the steps of how to transform a system call into assembly and how to extract the opcode sequence. Now to see if your shellcode works, compile and run these commands on the shell runner binary. So I'm going to give another 10 minutes for this. If there's any questions, please let me know. Okay, I think I'm gonna move on just because we're running out of time again. Uh, is there any questions or anything that you really want to know? Otherwise, I'm gonna move on into the solution. It shouldn't take you this long. Or sorry, it shouldn't take you that long. My bad. It shouldn't take you that long. You've already done previous system call, and I think you should be able to get the gist by now of how to transform system calls into assembly code and get the opcodes. Anyway, why? Okay, first of all, let's talk a little bit about some of these commands in the makefile. Why chown and chmod? The chown is to change the owner of the binary to the root user. So once you run sudo chown root shell runner, then shell runner is going to be owned by root. Chmod. Chmod adds the set UID bit and runs the program with privileges of owner temporarily. That means that when you execute shell runner, you'll have temporary root privileges. Okay. And then once the program is finished, then you no longer have root privileges. And now, if done correctly, like if you do this shellcode correctly, a normal user can spawn a root shell, which is pretty spooky if you think about it. Okay. Also, something I forgot to mention that I should have mentioned is that if you did this system call correctly, then it's going to segfault if you just run shellcode. It won't segfault if you run shell runner with these chown and chmod. But just running the shellcode by itself will segfault. And that's because shellcode itself doesn't really have any privileges it can maintain. Okay, so now let's talk about what is set REUID. Let's look at the man page for it. Set REUID. Okay, set real and or effective user or group ID. So essentially what this is doing is it's maintaining the privileges of the program. What does that mean? It means that because we gave this program the set UID bit here, we give it the set UID bit with this number, and it is also owned by root, it means set REUID is going to maintain those privileges when we spawn a shell. So let's do it. Okay, I'm actually just going to go straight to my solution just because, well, like again, we're running out of time. I don't want to hold everyone up. Okay, so let's go to exercise 3. So this is what you should have ended up with. The system called for set REUID is going to be 113. And then you can just XOR RSI and XOR RDI, right? That's going to give you no null bytes, I think, and it's also going to give you 0, 0, which is the arguments you need. Okay, so let's look at shell runner now. Shell runner. This is the opcode sequence. Let's see if we have any null bytes. No, we don't. Here's the opcode sequence. It's the exact same opcode sequence. If I try to just run shellcode, it's going to segfault, right? But if I try to run shell runner, I am now root, which is, again, kind of scary. Like, I have full access to pretty much anything now. Anything in my system. I own this system. Okay. Now for any questions? Hello, Messer Technologies. Okay. If there's no questions, I'm gonna keep moving forward. Okay. So I talked about that, okay, now let's talk about the final part. Let's actually try to execute shellcode in a buffer overflow. Now you can put it all together. So again, if you remember the Rob chain workshop, this is a bit similar. We want to build a stack, our own stack. So it's a similar idea here when injecting our shellcode, and we overwrite the return address to the start of the shellcode. But like, what if we don't know the exact address of the buffer, right? Then it's kind of hard to just guess. It's it's hard to just guess where exactly your shellcode starts so that it doesn't execute some bogus command in seg faults. So we're going to introduce what's called a no-op sled. A no-op sled, if so, does anyone? Well, hopefully people remember, but no-op is uh, the assembly instruction no operation, which means do nothing. So it does literally nothing. And that translates to the hex code, opcode 0x90. So what we're going to be doing is we're going to do a bunch of no-op instructions, our shellcode injection, some leftover padding, and then overwrite the return address to somewhere in here, somewhere where the shellcode, where the no-op sled starts. It doesn't have to be specific because, again, our no-op sled sort of just lets us slide in because it's a bunch of no operations. So it doesn't matter which order. So it's going to execute the no operations all the way up until it hits our shellcode injection, which is the important part. That does need a specific order, and that's going to execute our shell for us. So for exercise 4, I don't think we'll have time, but uh, I think I might just go over the solution. I'm gonna finish talking about this, but please let me know if you want me to give you some time to do it and go over the solution, or just go over the solution. But anyway, this exercise puts everything together to spawn a root shell from a buffer overflow as a normal user, which again is really scary. The makefile provided disables ASLR just to make it a little bit easier to do this exploit. ASLR is address space layout randomization. It basically just defense mechanism in order to prevent attacks like this. It shifts addresses around to make it even harder to just guess the address. So make sure to read the comment in the makefile to turn ASLR back on after you turned it off. Okay. So for exercise 4, you're going to analyze the overflow.c code and spawn a root shell using the shellcode you've built from exercise 3. Some useful tools are GDB. And what you need is an approximate address of where the buffer starts, your leftover padding, a no-op sled, and shellcode. Now, do you guys want me to go over the solution, or are you guys okay with staying over time? Okay, I think I'm going to go with the solution. Okay, let's just go through the solution then. Let's go exercise 4. Okay, let's go into exploit.py. Okay, so here we are just going e equals elf to overflow. So we're just mapping the overflow binary, right? Overflow, which has set UID bit and it's owned by root. Then we are just creating a process called ./overflow. We are having some padding. So if we look at the code for overflow.c, we have about 100 bytes, right? And the program seg faults at 120 bytes. So we have 120 bytes to work with, plus the 8 bytes for the buffer address. So I've made this a little bit easier by printing out the buffer, where the buffer address starts, right? So we're actually here, this line, all it does is it's receiving this address into the program, and it's converting it to P64, which just means Little Indian, and making it into a easy to inject format, I guess you could say. Then we have a bunch of no-op sleds. a bunch of no-op instructions, which is our no-op sled. So here we have, and then we have a shellcode, which is 35 bytes. So calculating everything, we have a 40-byte no-op sled, which comes first. Then we have our shellcode, which is 35 bytes. And then we have 45 bytes that are left over. If you calculate this number, it's going to be 120. And then finally, the last 8 bytes are reserved for the buffer address. So what this is going to do, if we do python exploit.py, it's going to spawn a shell for us. And who am I? Root. I am root. Is there any other questions? If not, that's going to be the end of this workshop. Oh yeah, I guess one more thing. If you're still interested in binary exploitation after this, I would recommend reading about return to libc exploits. These type of exploits are based on return-oriented programming and are actually able to beat defense implementations like ASLR. Be warned though, because it does require a bit of a deeper understanding about how ELF files are structured. Anyway, that's going to be it for this workshop. Like I said, if you still have any questions or if you want to know anything else, please ask. I am Groot. Yes, I am Groot. Okay, I think I'm just going to end the workshop now then. All right, thanks for coming and have a good evening, guys. Be at the MacPy CTF, please.